In the hustle and bustle of our daily lives, it is all too easy to take for granted the little miracles of the modern world. And yet, behind the ordinary objects which fill our lives are some extraordinary stories. Because each of these everyday objects conceals another secret industrial marvel. Concrete, the cell phone, light bulbs, steel, and traffic control. 5 ordinary things, 5 extraordinary stories, now revealed as we go behind the scenes inside the machines to find out, how do they do it? The Earth, the most wonderful of natural wonders. Coral reefs, grand canyons, breathtaking mountain ranges. It has taken nature many millions of years to form these geological marvels. Man, however, is not so patient. In every town and every city all over the world, architectural wonders are going up faster and taller than ever before. And what does every one of them need? Concrete. Concrete is the stuff of both extreme engineering and sidewalks. It's so universal that next to water, it is the world's most heavily consumed product. It may seem like a rather ordinary thing, but don't be fooled. Its manufacture involves a story of explosives, giant quarries, huge ovens, and a race against the clock from beginning to end. It's dawn in Tarragona, Spain. Here, concrete is being used to extend a local pier. What makes this project different from the rest is that it is creating some of the largest concrete blocks ever built. Measuring a phenomenal 60 meters long, 45 meters deep, and nearly 30 meters wide, each block takes up the space of 30 Olympic-sized swimming pools, stacked one above the other, and weighs in at 30,000 tons. Each one will be sunk into position at the end of the pier. But this block does not always look like this. It started 10 days ago as a metal platform, like a giant wire brush, which was towed underneath this amazing piece of engineering. It may not look like it, but we're beneath a ship. The Kugera. It's a giant concrete block maker that travels all over the world. But what is concrete? And how can you turn it into super-sized blocks? How do they do it? Surprisingly, the main ingredients of concrete can be found all around us. Rock. Different kinds of rocks help give concrete its strength. They're known as aggregate in the trade. In fact, the average family in Britain consumes 3.5 tons of rock every year, without even knowing it. That's the equivalent to a carload. And believe it or not, it's in everything from glass to toothpaste and chewing gum. You could say there's a little bit of concrete in all of us. Concrete is a mixture of aggregate, sand, water and cement. And the process of making those ingredients starts with a bang. This is the Lafarge Mount Sorrel quarry in central England. At 750 acres, it's the largest producing granite quarry in Europe. At 0.5 kilometre deep, it turns out 5 million tons a year. Aggregate, like granite, gives concrete its strength. And the dangerous business of getting it falls to the explosives team. Every day, the blasting team pack 4 tons of explosive into 12-metre boreholes, carefully drilled into precise places in the quarry face. Then, the blasting site can be filled and wired. Only by staggering the detonations by milliseconds can the powerful vibrations that travel through the rock be reduced. Once the explosive and detonators are set, the site is cleared of everyone except one person. The detonator. The only thing separating him from loose-flying granite is this steel can, 20 meters from the blast site. If all goes to plan, he'll bring down a 16,000-ton wall of granite by the push of a button.
Clear, mate. Yeah, clear down here. Yeah, clear here, right?
Once the dust and debris has settled, the detonator needs to check that all the charges have gone off. Now the granite's out of the rock face, it still has to get to the top of the quarry. And that's an 18-minute uphill climb-a-thon. Once loaded up, the full weight of the truck and the granite is over 100 tons. Waiting at the top of the quarry is the largest crusher in Europe. This grinds down the 30-ton load of granite in 20 seconds. Back in Tarragona, aggregate is just one of the ingredients needed to make up concrete. Without the next, the concrete would not be able to stick together. Cement. As the dew settles on the early morning Staffordshire moorlands, this huge factory in the heart of England churns out millions of tons of cement every year. Like the granite, limestone is blown out of a quarry and then works its way down a conveyor belt at 1,000 tons an hour to the cement works. The limestone is mixed and ground with another rock called shale. This floury mixture is known as raw meal. This is basically uncooked cement. The raw meal works its way through a series of cyclones, each one getting hotter and hotter until they find a way into a huge 58-metre-long kiln, where the fine powder is then cooked at 800 degrees Celsius. At this temperature, a chemical reaction happens between the limestone and shale that binds them together. This is the heart of cement making. It's in the kiln at this temperature that the raw meal changes altogether to become clinker. It's this chemical reaction that gives cement its strength. The problem is, if the clinker was just ground down into a powder, it would flash dry, set in seconds, no use to anyone. So it has a conveyor belt ride to a solution. Incredibly, yet another rock, gypsum, has the ability to act like a delay switch. The gypsum and clinker are ground into a huge rolling oven, and finally, what emerges is cement.
Nearly 20 million tonnes of cement produced in my lifetime here. And the funny thing is, for a complex process, all you end up with at the end of the day is a bag of dust.
But that bag of dust is essential to the Kugera. Without it, it cannot produce its giant blocks. But here's the rub. Concrete sets very quickly. So, the aggregate, sand and cement can never be mixed together more than 5 kilometres from where it's used. Any further, and it's too late. Game over. Can't be poured. At the Kagera, the pouring of concrete is no less tense, going on day and night, rain or shine. If the concrete is poured too quickly, it won't bond properly with the previous layer. Too slowly, and cracks will appear. Either way, the whole block will have to be scrapped. And they only have a couple of hours before it sets too hard to fix. For 10 days and nights, concrete has continuously been poured from mixers working round the clock. Now the concrete is firm enough to finally be broken free from the Kagera. However, there is an additional twist to the story. This giant concrete block is going to have to float. 2 tugboats have come to tow the block away. But how is this possible? It may not look like it, but the Kagera's walls are hollow and filling fast with water. As the ship sinks, the water displaced should lift the massive brick off the seabed. And thanks to hollow chambers inside the brick itself, in theory, the thing should float. Now this colossal brick can be towed away. As the water floods out of the Kagera's walls, it rises once again, ready to make the next giant block.
Maybe 100 square. I'll be here for about 10 minutes.
30 years ago, it was just a fantasy, that from wherever you were, you could phone somebody anywhere on the planet. Now, it's a reality. Yet how we do this is nothing short of a miracle. A miracle we don't give a second's thought to, thanks to the cell phone. The first mobile phones were bulky and impractical. The batteries weighed a ton, and then they didn't last very long. The circuitry in the phone took up loads of space, and the aerial was long and awkward. Today, every cell phone fits into the palm of your hand. But have you ever wondered how they've managed to become so small? How do they do it? To answer this, we turn to Finland, because it has become a cell phone technology hotspot, thanks to manufacturing giant Nokia. In the town of Salo, 2,000 people make some of the 500,000 cell phones Nokia sell each day around the globe. The secret to the cell phone size is how they manage to fit up to 350 components accurately onto one tiny circuit board. What starts as empty circuit boards work their way along a 30-meter conveyor belt. First stop, the secret to getting all the electrical components on the board, the mounting machine. Pinpoint accuracy every time means more digital circuitry on the board. More circuitry means more functions. And it's fast. 80,000 components an hour. Each set of components arrives as a coil, a bit like celluloid, ready to be fed into the boards. The circuit board is the brains of the cell phone, housing all the microprocessors and memory functions. The computer chips inside a cell phone have lots to do. They convert the dialogue from analog to digital. Another calculates the signal. Another handles the keyboard and display. At super speed, everything is checked against a photographic map for accuracy. One component in the wrong place could stop a signal or overheat the phone. In such a tiny space, there is no room for error. A black and white camera picks up the slightest degree of change of position, so it can be corrected by the mounter. As the board moves along the line, it builds up the circuitry. The problem is there are enough components to fit onto 2 circuit boards. So what do? They turn the board over. Because the antenna is hidden away within the phone, radio waves can interfere with the circuitry. So another little trick comes into play. Tiny protective metal shields are placed around the components. Now comes the assembly. LCD displays, cameras, the keypad. For whatever language the phone's destined for. English, Greek, Arabic or Hebrew.
I always have my phone with me. I don't know anyone who doesn't use a cell phone. I would feel naked without it. I feel safe. I couldn't imagine living without a cell phone.
Inch for inch, the cell phone is one of the most powerful computers we play with on a daily basis, processing millions of calculations every second. They may all look the same, but each phone has a unique number which sets it apart from every other. Once it has this, it's ready to be used. But how do they work? Radios use a single frequency. That means you can either talk or listen. Cell phones get round this problem by operating on 2 frequencies. When you make a call, one frequency is taking the voice of the caller to the transmission tower, and the other is sending the other person's voice from the receiving tower.
No terve Mario, missä sä oot?
No terve, tässä on Mario. Hei, mä oon pahoillani, mä oon aika lailla...
So a cell phone uses both frequencies simultaneously. It's a brilliantly simple idea that relies on a series of transmitters that work an area called a cell. And that's where the term cell phone comes from.
Okay.
Each cell can manage thousands of frequencies. Because transmitters use only a small amount of power to communicate, a lot are needed. This small detail is more important than you might think.
Moi moi.
It's because cell phones don't have to transmit over long distances that they don't need heavy batteries or bulky aerials. It's this vast transmitter system that allows cell phones to be so small. And the future of the cell phone is set to revolutionize our lives even more. In downtown Helsinki, all kinds of new developments are being tested. Here, they pay for the tram by cell phone. The Finnish people are also very concerned about beating traffic jams. So, what better way than to check how busy the highways are than by tuning in to the closed-circuit TV cameras over the rush hour hotspots. Looking good so far. The cell phone could see the end of paper money and credit cards altogether. As more and more features fit into our phones, the world's appetite for the cell phone is ever increasing. In Salo, Finland, a warehouse filled with millions of phones is preparing to meet that demand. As day turns into night around the world, it springs into action. Few inventions have changed our lives so profoundly as the electric light bulb. What the light bulb has done is nothing short of revolutionary. It has extended our day into night and allowed us to carry on at our increasingly manic pace. Light bulbs are such a necessary part of our lives that annual sales exceed $4 billion in the US alone. They can even be seen from the moon. But have you ever stopped to think how they produce the lights we take for granted? How do they do it? Light bulbs seem such a simple design. Tiny wires coiled and mounted inside small glass bowls. But look again. Each twisted filament, made of tungsten metal, heats up to an incredible 2,500 degrees Celsius, enough for the tungsten to generate a glowing white light, and hot enough to melt gold. The light comes from electricity passing through a delicately coiled wire circuit. The thicker the wire, the greater the amount of energy that can pass through it. Yet the one thing that would put an end to this incredible reaction is oxygen. Oxygen is the enemy. It would make the tungsten burn out in the blink of an eye, which is why the glass bulb is so important, something the manufacturers know all too well. One of the biggest factories in the world making the classic shape standard bulb is the Philips factory in Pila, Poland. 3,600 people work here, and because the demand for their bulbs is so great, they work in shifts that go on 7 days a week and 24 hours a day. Something they wouldn't be able to do without light bulbs, of course. Last year, they made over 500 million bulbs, using enough tungsten to travel to the moon 12 times. Here, the production of the light bulb doesn't start with the metal filament, it begins with the bulb itself. Glass is made from a mixture of lime from limestone, potash, a kind of natural soda, and sand. And the factory gets through tons of the stuff. Lime stabilizes the glass as it melts, and the potash reduces the temperature needed to melt it. Thousands of tons of sand are used every year. All the ingredients are mixed together and fed into a giant furnace, the size of an office block. But one final magic ingredient is, rather surprisingly, glass itself. Recycled broken bulbs, known as cullet, actually speeds up the melting process, reducing the amount of energy needed to melt down the ingredients. Even with the cullet, they need to reach temperatures of 1,600 degrees centigrade, hotter than molten lava. Inside the furnace, as the materials are poured in, they melt almost immediately, and a funny thing happens. At this heat, a natural convection current makes the molten glass slowly move down through the kiln, all by itself. The molten glass leaves the furnace and is poured into a moulding machine. High-pressure pumps blast air into the bulbs to form their final shape and smooth the glass out inside the mould. At this stage, the glass is still very much a liquid. But there's a delicate balancing act going on here. If the glass cools too quickly, it will shatter. So, each bulb is spun out onto a long conveyor belt and taken through a series of cooler and cooler ovens, which slowly cool down the bulbs to 90 degrees Celsius. And this reveals the Achilles heel of glass. It is very breakable. Why its rough handling doesn't shatter it at every stage seems unbelievable. However, Philips have devised a series of crude but effective techniques for making sure this doesn't happen. Firstly, a shaky conveyor belt. Okay, sounds crazy, but this vibration machine singles out the bulbs and picks out the weak bulbs from the buff bulbs. If it is too weak and cracks under the movement, it drops down under the conveyor belt. It's like evolution. Only the strong survive. And those that don't go back into the furnace as cullet. It's a cycle that produces 50,000 glass bulbs an hour, and that means a phenomenal 15 every second. This waterfall of glass has a secret to it. Each time there is a drop, it is never long enough to create any damage. And this happens at lots of places throughout the conveyor line. And it's not just standard bulbs that are made here. The factory makes over 300 different types. The production of the fluorescent tube involves a totally different procedure. Pulling molten glass straight out of the kiln, spinning it into a tube shape, and then dragging it 50 meters along a conveyor belt to make one giant glass tube. These are then cut and heat treated to turn into the correct sizes.
For 12 years, I've been making fluorescent lights. In that time, I've made 108,000 miles of tube. That's 4 times around the Earth.
As the drama dies away on the fluorescent line, back with the standard bulbs, a conveyor belt leads them onto the next stage of their story. At the moment, they are just empty shells. Soon, if all goes to plan, they will contain light. And how they do it is amazing. It's an incredible thought that simple chemicals and metals are all that have transformed an idea from over 100 years ago. That electricity could create sustainable light into a light bulb. Making the inside element of the bulb involves a ballet of machinery. It brings together what are called the glass stem, the leading wires and the holding wires. Eventually, these all work to hold the tungsten wire in place. The stem is heated up so it gets to a melting point where the wires can be added, and then it is clamped and gradually cooled to reduce any chance of cracking. This is what inspectors don't want to see. Small purple lines mean the glass is potentially weak, and if so, then it's back into the furnace for the stem. However, before the marriage of the stem inside the bulb can take place, there is still one crucial thing missing: the tungsten filament itself. Tungsten is the only metal capable of producing light continuously. Any other metal withers after minutes, or at best, a few hours. And astonishingly, it has not changed as the main ingredient of the light bulb since Thomas Edison perfected its potential more than 120 years ago.
The filament in the light bulb is made of wire. When stretched, it's 1 metre long. People don't realise how many machines and complex processes are needed to make it.
The problem has always been that most metals melt before they reach the high temperatures needed to produce light, or they burn out too quickly. But not tungsten. Tungsten shines white when heated at 1,300 degrees Celsius. The problem with tungsten, however, is it can't be anywhere near oxygen for it to work. This is why the bulb is crucial in keeping it in a vacuum. And there are 2 secrets to how the tungsten filament can outshine any other metal. Firstly, once it's attached to the stem, it's dipped in gether, a chemical that will burn off any remaining oxygen inside the bulb at the moment it is first lit. Before the second secret can be revealed, there is a marriage ceremony. The stem and the bulb are finally joined together. The second secret is that once the bulb is sealed, a gas called argon is pumped in. This pushes out any remaining oxygen and increases the life of the tungsten. But it's not foolproof. There is still a chance the oxygen will find a creepy corner to hide in. Seeing whether it will light or whether any oxygen is left to burn out the tungsten, we'll have to wait. Just before the bulb is lit for the first time, the cap is fixed and welded to the lamp, and the contacts are soldered on. Now the moment this bulb has been waiting for, when the lamp is lit for the first time. It has been a long journey from the furnace and along all the conveyors. If the process has worked, there will be a puff of smoke from the gether and the bulb will be oxygen-free. If not, the bulb will blow. Witness the birth of the bulb. Factory manager Gregor Lazinchik prowls the plant like a bear, listening to the song of all the machines at work. And there is something he finds amazing.
Every day I watch the product that has been around for 120 years, and every day I wonder why it's changed so little, whilst the production process has changed so much. So much time, so little changes.
But change is on the way. After all this technology, design and manufacturing effort, incredibly, the standard light bulb is, by today's standards, hugely inefficient. It is an energy-sucking device that converts just 5% of electricity into light. The remaining 95% of the energy is wasted heat and infrared light, invisible to the human eye. Other kinds of bulb are being designed to be far more efficient. Fluorescent bulbs last 20 times longer and give off 75% more light. Each one is a chemical chamber, also producing invisible UV light. But with fluorescent light, a phosphorus powder coats the inside of the tube, and this reacts with the chemicals to produce visible light. But light bulbs of the future could depend on the same chemical that keeps diaper rash at bay, zinc oxide. This could help convert electricity to light 10 times more efficiently and last 10 times longer than the standard bulb, reducing the planet's electricity consumption by more than half. In the US alone, that's a saving of $35 billion a year. So, soon the classic traditional light bulb could be phased out altogether. Even within their lifetime, the people who have made this deceptively simple masterpiece could be talking about the light bulb as a museum piece, an antiquated icon of the 20th century. Trains, trucks, cars, bridges, ships, aeroplanes. What do they all have in common? Steel. What else is steel a part of? The answer is everything. Even if something is not made from steel itself, it has been made by something that was. Every product on the planet has involved steel somewhere in its production. Like bronze and iron defined previous ages of man, so steel defines ours. So, how do you make the product that the world cannot do without? How do they do it? Steel looks like such a natural thing that you would be forgiven for thinking it came out of the ground that way. In fact, there is no natural metal called steel. To make it takes a kind of modern-day alchemy. And it all starts with iron. Iron is the basic ingredient of steel. And it's found in rock. Rocks that are rich in iron ore are mined all over the world, ground down and shipped to the steelworks. And in the English town of Scunthorpe, it takes 4 queens of England to turn it into steel. Introducing Anne, Mary, Bess and Victoria. These are the 4 furnaces at the Chorus Steelworks. And here, a pulverized rock begins a journey of transformation. Iron ore is basically iron oxide, or iron, chemically bonded to oxygen. The problem is, to make steel, you need to get rid of the oxygen and separate the steel from the rock. To do this, you need to melt it. The iron ore is hauled up to the top of the furnace in containers the size of garbage trucks, and then dropped into the furnace. Then, a huge amount of hot air is blasted up through the iron ore, and this is where the blast furnace gets its name. The rock is melted at a temperature of 2,000 degrees centigrade. It's amazing to think that what looks like lava only a few hours ago was solid rock. No longer iron ore, now it's molten iron. From here, the iron is poured into a train. No ordinary train, of course. This is called a torpedo. They are specially insulated to carry the 1500 centigrade molten iron. Every day, 10,000 tons of molten iron is moved to the part of the plant that will turn it into steel. The iron is poured into a huge drum, which can hold 350 tons of iron in one go. It looks like liquid fire, but incredibly, in only 30 minutes, this molten iron will be turned into steel. And it takes just 3 steps. Step 1. Add scrap metal. This is going to help control the temperature the vessel gets to. Step 2. Pour the iron on top and mix in a secret ingredient. Lime. Sounds like a cocktail. It's going to be more like a volcano. Step 3. Add oxygen. Sounds simple. Well, what's actually happening inside this container is like turning lead into gold. The problem is that there are impurities in the iron, like carbon, that will not make high-quality steel. So, an oxygen lance is lowered above the molten mixture. It blows in high-purity oxygen at twice the speed of sound. This turns the carbon into a gas and the iron into steel. As the top of the vessel opens up, it also shows a moment of manufacturing alchemy. Iron has been transformed into the product of our age. This also reveals the secret of the lime. Floating on the surface are all the other waste products, called slag, drawn out by the lime. Now we have high-quality steel bubbling beneath the surface. And tapped from the bottom of the vessel, the steel is seen for the first time. But it's at the next process that the molten steel is shaped to suit the jobs they are heading for. Rail tracks need long, thin steel. Pianos and suspension bridges need strong, thin wire. Cars and washing machines need sheets of steel. The hot steel goes through a process of water cooling as it's drawn through cooled rollers and water sprays. The outer shell of the steel may be hard, but inside it's still a molten liquid. Then the hot steel is cut to length by automatic gas burners. Even after it stops glowing red hot, it still takes several hours to cool down enough to be handled. Although they may not look like the steel objects we use, they soon will. Ready to make every other product on the planet, steel has the weight of the world on its shoulders. And it's up to the job. Every day, the 3 billion people living in the world's cities are trying to get from point A to point B. Mass movements like this can cause huge problems. But the fact is, the congested rhythms of drive times and rush hours are a part of the everyday life of a city. It's a constant battle to keep the people moving, the buses running, the trains on time, to keep the city working. But if you think it is just you that is deciding your best route to work, or even whether you should turn right or left, you're wrong. There are other forces influencing the roads you take or the speed you travel. You are a part of the largest orchestra ever conducted. And how do they do it? Well, it all starts with the traffic light. In Poole, on the south coast of England, traffic light manufacturer Siemens is developing ways to take the traffic light into the 21st century. Everything from super efficient lamps to the brains of the traffic lights, the circuit board. So, why does a traffic light need a brain? Because they talk to each other. At this London junction, there is a traffic light. There is also a piece of wire buried just beneath the surface of the road. This wire forms a circuit. When traffic passes over it, a signal is sent to a box at the side of the road. The circuit board is counting the number of cars passing through the junction. And if the traffic gets too busy, it will allow for more green time to alleviate the congestion. This system is called Scoot, and it's monitored by the secretive conductors of London. Introducing London's Traffic Control Centre, the LTC.
Kew Bridge is looking slow.
Have we assessed what's going on at Park Lane?
An incredible 21 million journeys take place across London in any one day. And you may not realise it, but these guys are managing every move. Using 5,000 traffic lights and 1,200 CCTV cameras positioned all over the city. With them, traffic can still be pretty sticky, but without them, gridlock. And today is the largest street festival in Europe. 1 million people have descended on Notting Hill. All the roads have been closed. And because there is no traffic except a procession of festival floats, it's the domino effect on the rest of London that's the problem. And the LTC have one mission.
We don't have much to do with the actual event. We are managing the network outside the event.
The controllers monitor where the traffic that would have gone through Notting Hill is actually going. To keep the traffic moving, they can change the timing patterns of the lights, give more green time to congested side streets, increase red light to create more open roads, use road signs to divert away from problem zones, then try to predict and react to the domino effect to the rest of London. It's an amazing piece of orchestration that happens every day. At least that's what they say. Through the endless cycle of days and nights, the Earth moves on. The world never sleeps. Somewhere, somehow, someone is at work. Producing, manufacturing, distributing. Since this programme began, worldwide, 200,000 tonnes of concrete have been produced, 27,000 people have bought new cell phones, 14 million light bulbs have rolled off production lines, and the number of cars on the planet has got closer to an astonishing 450 million. Even the most ordinary things have an extraordinary story to tell. We only have to watch and listen.
接下来，美国顶尖的爆破专家必须争取时间，设法要在弗里蒙炸弹客下一次作案之前阻止他。剑士破案之集接着播出。